Have you ever looked at a tiny computer chip and just wondered how it actually works? How we get something like the classic 8051 microcontroller to do, well, anything at all? It all comes down to speaking its language. And today, that's exactly what we're going to do. We're taking a tour of its native tongue, the 8051 instruction set.
So really, how does a computer actually compute? I mean, it seems like magic, right? But it's not. It all boils down to one simple idea: following a list of incredibly basic commands, one after another, at a mind-boggling speed.
And that list of commands, that's what we call an instruction set. You can think of it as the processor's entire vocabulary. Every single thing the chip is capable of doing is defined right here. It's the language we use to speak directly to the silicon itself.
Okay, so here's our game plan. We'll start with the basic grammar of the language. Then we'll see how it moves data, how it crunches numbers, how it makes decisions, and finally, how all these tiny little pieces come together to create something amazing.
All right, first things first. Let's look at how you actually structure a command in 8051 assembly. You know, just like any language, it's got rules, a grammar you have to follow to make sense.
So, every instruction pretty much looks like this. You've got the mnemonic, which is the actual command verb, like mov for move. Then you have the operands, which are the nouns, the things the command acts on. So an instruction like mov r1, #25h simply means, hey, move the hexadecimal value 25 into a tiny storage spot inside the chip called register R1. Just think of registers as the chip's personal super-fast scratch pad. Now, before you can do any cool calculations or make any smart decisions, you got to get your data in the right place first. That's what data transfer instructions are for. Honestly, they're the foundation of, well, everything. And the undisputed king of data transfer is the MOV instruction. This thing is the workhorse. Its job is simple: copy data from a source and paste it in a destination. You'll see this one more than any other for sure. So, let's look at our example again. MOV R1 #25h. When the processor sees MOV, it knows it's time to copy something. It identifies the source, the value 25 hex, and the destination, register R1. And boom, after that instruction runs, R1 is now holding that value. Simple as that.
But here's where it gets interesting. MOV is your general-purpose tool, but the 8051 has specialist tools for different jobs. Need to grab a value that's part of the program's actual code? You use MOV, C. Need to talk to an extra memory chip sitting outside the microcontroller? That's a job for MOVX. And if you just need to save and grab data real quick, you can push and pop it from a special area called the stack.
Okay, our data is where we want it. Now for the fun part. Let's actually do something with it. It's time to look at the instructions that are basically the processor's built-in calculator.
Let's start with addition. The add-d command is super straightforward. It adds a number to a special register called the accumulator, which is basically the main workspace for all math. But what if your numbers are bigger than what one 8-bit byte can hold? Well, that's what ADDC is for. It does the same addition, but it also adds in any carryover from a previous addition. This lets you chain them together to add really big numbers. And of course, there's a whole toolkit of other math commands. You've got INC and DEC for quickly adding or subtracting just one. There's SUB, which is the subtraction version of ADC, letting you do complex subtraction. And here's a big one: you have dedicated instructions for multiplication and division. That's a huge deal, because not all simple processors have that.
But it's not just about math. The 8051 can get down to the level of individual bits. These logical operations AND, OR, XOR are absolutely crucial for things like checking if a sensor's on or turning on a single LED. You can even flip all the bits in a byte with CPL or shift them all around with rotate instructions. It gives you incredibly fine-grained control.
So we can move data and we can process it. But how do we give our program a brain? How does it make choices or repeat a task over and over? That's where program control instructions come in. This is how we create intelligent behavior.
The most basic way to control a program's flow is with the jump. Instead of just running the next instruction in line, a jump tells the processor, hey, stop what you're doing and go over here instead. And the 8051 gives you a classic trade-off. SJMP is small and fast, but it can only jump a short distance. LJMP can go anywhere in the entire memory, but it's a little bigger and slower.
Jumps are cool, but where they really start to shine is when you combine them with a condition. That's how you create loops, doing something again and again. And the 8051 has this one fantastic instruction that makes it ridiculously easy. Check out this little piece of code. We start the accumulator at 0 and load the number 10 into register R2. That's going to be our counter. Then we have a label called again. Here, we add 3 to the accumulator, and then comes the magic part. DJNZ R2 again. That one single line is the engine that drives this entire loop. So what's DJNZ actually doing? The name kind of gives it away. Decrement and jump if not 0. So first, it subtracts 1 from our counter in R2. Then it asks a simple question, is R2 0 yet? If the answer is no, it jumps right back up to the again label and the loop runs again. It's only when R2 finally hits 0 that the loop stops and the program moves on. Just brilliant. It shows how one simple instruction can create complex, repetitive behavior.
Okay, let's step back for a second. We've seen how the 8051 moves data, does math, and controls the flow of a program. Let's see how all these simple commands come together to create literally every complex action we depend on.
You know, everything we've talked about falls into one of these 5 main groups. You've got data transfer for moving stuff around, arithmetic for doing the math, logical and Boolean for flipping individual bits, and branching for jumping around and making decisions. That's it. That's the whole toolkit.
So, just how big is that toolkit? The entire instruction set, the complete vocabulary of this powerful little chip, is just 255 instructions. That's it. I mean, think about that. Every single program, from a simple blinking light to a complex robotic controller, is built using just these commands.
There's a real elegance to that, isn't there? It's this perfect example of how combining simple, solid building blocks lets you create something way more complex than the sum of its parts. It really is like having a small but incredibly powerful alphabet for writing the language of machines.
And that's the key takeaway here. You now get the basic language of a machine. You've seen the verbs, the nouns, the grammar that brings a piece of silicon to life. It's not magic at all. It's just a language.
Which really just leaves us with one last question to think about. Now that you've been introduced to the language, now that you know the basics, what would you tell the machine to do?